Okay, so as I mentioned before, there are two limit definitions of a derivative. And so this is still 3.1, but we're talking about the second limit definition of a derivative. And recall that a derivative is the slope of the tangent line. The problem is a tangent line only crosses a curve at one point. So again, I have our Desmos example up from the other day. My tangent line is the purple line and is touching my red parabolic curve at 1 point, 3, 0.25. And it's hard to find the slope at just 1 point because the slope formula requires 2 points. Okay, and so we talked about the fact that we could estimate the slope of the tangent line by picking values, 2 points on a secant line, and then choosing x values that get closer and closer to that point of tangency. Okay, so for example, my 3 would be the a value. So as these x values of 3.9, 3.83, etc., as those x values approach this a value of 3, I'm going to find the slopes of these, successive secant lines. Until I pick x values that get so close to that a value that the secant line basically looks like the tangent line, okay? And I would be using the slope of that secant line to best approximate the slope of the tangent line. Okay, well, there is another way to approach this. And the other way to approach this is to talk about the distance between these x values. Okay, so the first limit definition of a derivative talks about picking x values that get closer to the given x value, okay, as these x values approach a. The second limit definition of a derivative talks about the distance between these x values. And so when I take a look at my example here, if I have the point 3, 0.25 and the 0.64, I'm going to be looking at the distance between these x values, okay? And the distance between these x values is h, okay? So I would say 3 plus h is 6. Okay, and in this case, my h would be 3. The distance between these two x's is 3. But 3 and 6 are really far apart. In fact, that secant line looks nowhere close to the tangent line. So again, the idea is to pick x values that get closer and closer and closer. So let's go with 4. Okay, so my next set of points would be, again, 3, 0.25. That's my point of tangency. And now I have the point 4, 1. Well, again, this time, instead of talking about my x values being chosen so they're closer to this a value of 3, I'm going to approach it as the idea of the distance between these, okay? And so, again, 3 plus h would equal 4. Well, in other words, the distance between these two x's is 1. Okay? And so on. I'm going to choose another point that continues to move closer. Let's see if we can get 3.5 in here. That's pretty good. All right, so again, now I have another set of points that are being compared. Again, my point of tangency, okay, along with this new point, 3.5, 0.563. And again, instead of focusing on the fact that my x value of 3.5 is getting closer to 3, I'm going to look at h, the difference between them. So 3 plus h is equal to 3.5. And again, h represents the distance between these x values, and that distance is 0.5. And what you should notice as we're moving along here is that my h, the distance between these x's, is getting smaller and smaller and smaller, okay? So again, what we're identifying is this h, this distance, so this is h, the distance between these x values. And so we're approaching this as find the slopes of the secant lines as h approaches 0. And again, I just want to qualify because I have yet to do this. H is the distance between the x values. Okay, so again, as I choose x values that move closer and closer to 3, the gap between those x values is getting smaller. The hope is that I would end up choosing x values. So again, here's my point of tangency. And then choosing an x value, whatever that y is. At this point, it doesn't matter to me, okay? Choosing an x value so that that h, that distance between those x's, 3 plus h equals 3.01, that h, again, continues to get closer and closer to 0. So we can think of this as another way. So we can think of finding the slope of the tangent line, right? We represented that by saying f prime of 3. We could say f prime of 3 would be the limit as h approaches 0, as the distance between the x values becomes smaller and smaller and smaller, okay? And again, I would have to qualify this as, let me label these here, okay? This would be my a value, and so then this would be my a plus h value, right? Here's my a value 3. Well, 3.01 is 3 plus my h, my 0.01, okay? And then this would be f of a, and so the output here would be f of a plus h. All right, so I'm finding the limit as the distance between my x's becomes smaller and smaller and smaller, heads to 0, of my difference quotient, y2 minus y1 divided by x2 minus x1. Okay? And remember, in this particular case, we're using 3's, so we can go ahead and put some 3's in there. F of 3 plus h minus f of 3, all divided by 3 plus h, right? This is that second input here. 3 plus the distance between 3 and the 3.01 minus 3. That's this guy right here, okay? And what we should notice when we write this out is that this 3 minus 3 simplify. And so what I really have in this particular case is the limit as the distance between my x's head to 0, change in y. Well, when I simplify that denominator, I'm just left with h, right? Because 3 plus h minus 3 ends up being h. This is specific to the case over here in the Desmos. But we're going to say in general. In general, that second limit definition of a derivative, and that's what I started to do up top, f prime of a. For any a that I have, I would evaluate the difference of the outputs divided by the difference of the inputs. And what happens is that this a cancels with this a. Okay? And this would be specific to using the points a comma f of a. And that is our point of tangency. Okay? And the ordered pair a plus h comma, the output when I evaluate my function at that a plus h. And again, I just want to make the same comment that I did earlier. H represents the distance between the x value of a and an x that gets closer and closer to a. Okay? So another way to look at that. All right, so in class tomorrow, we will use this idea to practice setting up this second limit definition of a derivative.